Hi everyone, let's now discuss full octet resonance stabilized carbocations. So we know that a carbocation itself is going to be an incomplete octet carbon, right? It's an incomplete octet cationic species. Well, what we have is this observation that if a carbocation is directly bonded to a heteroatom, like an oxygen or a nitrogen or a chlorine or a bromine, that heteroatom could resonate its lone pair into the empty p orbital of the carbocation. Now, the result of that resonance is that the heteroatom will form a pi bond to that carbon, okay? And when it does so, the heteroatom will assume a positive formal charge. We'll look at examples in a minute. What's really important about that resonance is that it creates a full octet resonance contributor. That heteroatom in the positive state will be a full octet structure, okay? And it is, accordingly, the more stable resonance contributor. Okay, so carbocations are incomplete octet, but when that heteroatom resonates to stabilize it, it will form a full octet contributor. But that heteroatom must be directly bonded to the carbocation to engage in that resonance. Let's take a look at two examples. Here we have an example of a carbocation, and it's directly bonded to an oxygen atom. This oxygen atom can take a lone pair and delocalize it to form a pi bond with the carbon. When it does so, the oxygen assumes this positive formal charge, and between these two structures, this is the more stable contributor. And actually, this is a really stable structure. This would be even more stable than, say, a tertiary alkyl, okay? This full octet resonance is very, very stabilizing, okay? We love it. And this is the case that we would see this resonance from the heteroatom if it is directly bonded to that carbon bearing the positive charge, okay, if it's directly bonded to it. So this could be an oxygen or a nitrogen or a chlorine or even a bromine. Here we have an example of a bromine directly bonded to a carbocation. The bromine can resonate its lone pair and form a pi bond to the carbon. The bromine assumes a positive formal charge, and this is the more stable resonance structure because you have a full octet atom now. Every atom in the structure has a full octet, but on the left structure, your left contributor, that positively charged carbon, is incomplete octet. Now, comparatively, bromine wouldn't stabilize that positive as well as the oxygen, right? But both are full octet compared to the incomplete octet carbocation. So it's really important to be able to identify this in a question. Maybe you're given a ranking question or you're given a reaction and there's two possible carbocations that can form, but one has the opportunity to be full octet resonance stabilized. Well, that would be the more stable carbocation because you get that full octet resonance structure. So again, these heteroatoms delocalize their lone pair to form a pi bond with the carbon that was bearing a positive formal charge, and the result of that resonance is the formation of that carbon to heteroatom pi bond and the formation of a full octet resonance structure in which that heteroatom assumes a share in the positive charge.